Hey, have you guys heard about the new Parker Sporlan S3C case controller? Contractors, how about a case controller with a one-day setup, access to more data, and efficient system operation for the end user? The S3C series of case controllers provides contractors and store owners automated configuration and network integration. You can maintain precise food temperatures without supervisory control. Easily monitors to prevent product loss, and Bluetooth provides a local connection with the TechCheck mobile app. The series includes case controller display module, a valve supporting open protocol, communication via BACnet and Modbus. Sporlan's mobile app, the TechCheck, allows communication with the S3C case controller to enable proof of work, diagnostic, and data sharing. The S3C communicates with building automation systems and works with Sporlan's SPW series of pulse width modulation valves, also the SSR series of electronic expansion valves. Visit Sporlan.com for more information.
What the fuck is this?
Good evening, everybody, and welcome to Advanced Refrigeration Podcast. You're here with your hosts, Brett Wetzel and Kevin Compass. What's going on this week, Kev?
Oh, I'm down in your area, actually, down in wonderful Texas. Just taking care of some punch lists at some stores that the branch down here was having some issues with. So me and another one of my guys are down here basically going through a bunch of racks and knocking all these little issues they've had for a long time that they've had some issues solving. So we're down here, and then we're doing some training too with some guys. By you?
Just service calls this week, just cleaning up some stuff. Going through some old calls that needed to get taken care of. I got to play with a roll seal door for a little bit, which obviously was just because they hit it, and that's why it wasn't working. And then I'm going to be working with trying to figure out two issues with some screws tomorrow. But other than that, that's really about it. Really boring week.
Yeah, it was a pretty stressful week this week. It's stressful, and I'm not used to the heat down here and humidity. Monday was pretty miserable.
I was going to say, it wasn't...
not to mention all the tornadoes.
Oh yeah, when you texted me that night, my whole family was heading downstairs to take refuge in the closet underneath the stairs.
Yeah, we were drinking beers at the hotel bar, just waiting for waiting for the tornado to come. So, but all right, guys, tonight we're gonna go over Cascade CO2. So more so in the Cascade application, and then the next one we'll break into transcritical. So Brett, I'll let you take the lead on this since you guys have a lot more Cascade systems than us. So you want to go over the basic operation and setup of them? Weabsolutely.
So Cascade Subcritical CO2 is a lot like pump liquid. We're basically on pump liquid. You're trying to control a lower temp SST to maintain a certain pressure, a certain SST as far as your CO2 side. Typically, on most racks that are set up, you're trying to maintain anywhere from 20 to 25 degree CO2 going down all your cases. That is dependent on what your medium temp side is. These systems have to be balanced. So if you have a medium load that comes back that causes your pressure to go up, that's inherently going to cause your CO2 discharge vessel pressure to go up. The way these things are typically piped is the discharge of the CO2 goes into some sort of de-superheating coil. They want to get rid of a lot of the superheat coming off the coil because those heat exchangers aren't really meant to have 160, 180 degree discharge temperature going into them. So what happens is once the CO2 goes into a de-superheating coil, whether it be controlled with a fan, whether it be controlled with a three-way valve, some sort of way to basically bring the temperature down to whatever it was designed for. Most of these systems are designed for the heat exchangers are receiving approximately 95-degree CO2. You're still ranging anywhere from 440 to 460 psi on the CO2 side for the discharge for your compressors. But that pressure is going to go up based off of the basically the DX side of the heat exchanger on the medium temp side. So once the CO2 does leave the desuperheating coil, goes down to 95 degrees, that goes into the heat exchangers. You might have anywhere from 2, 3 to 4 heat exchangers, depending on how large the Cascade system is. But basically, the whole purpose of those heat exchangers, just like in pump liquid, we're trying to basically take that CO2, the vapor CO2, and convert that into a liquid. The pressures are basically dictated off of the other refrigerant that you have there. So basically, if you're running, let's just say you're running a 12-degree SST, most of those heat exchangers have a 7 to 8 degree TD. So basically, whatever temperature that you're putting in, it's almost like discharge air, but instead that's going to be the controlling temperature of the CO2. So if we're maintaining, 12 degrees to about 13 degrees saturated, if we have a 7-degree TD, that'll give us approximately 20 degrees. 20 degrees on CO2, if you use your PT chart, will actually equate to 440 psi. So that's what the vessel pressure control is going to be. Some of these systems have an auxiliary condenser on the side, basically another heat exchanger that is usually tied into a generator panel. Because like we had stated before, if you do have a failure with the CO2, whether it be an oil failure or power failure on the DX side, the pressure is going to go up on the CO2 side and basically start relieving once it hits anywhere, but usually about 585 to 635. There's usually 2 reliefs on there. One's one set for a little bit lower pressure, and then you have the backup just in case something else would happen. But basically, it's trying to control that temperature and that pressure of anywhere from 20 to 25 degrees saturated. Some manufacturers, some zero zone racks, some Husband racks, they want to control about 25 degree CO2. So basically, they have some EPRs on the DX side, basically either the 448, 449, or 513. And basically they're trying to control 18 degrees saturated, which if you give it 7-degree TD, that'll bring you up to 25 degrees CO2, which if you look at the PT chart, once again, it'll go up to 450 PSI. And, basically that's what we're doing. So it's a lot like pump liquid CO2. The only difference is that we're actually using compressors to actually circulate the CO2. So that's why we have to have the extra components, basically the desuperheating coil. We have to have the CO2 oil system. We have to have those cascades because like I said before, they have to be very even. If you get an increase in load on the medium temp side and your pressure starts delving up, that means your vessel pressure is also going to delve up because your saturated is going to raise. Well, the problem with that is that you have to be able to drastically be able to bring that down as fast as it's coming up. So basically, a lot of those compressors, at least one of those compressors on the medium temp side, the DX side, as well as the CO2, always is going to have a VFD driven. So that way it can compensate for that large influx of heat coming back from either the DX side or the CO2 side. Once again, if the DX side does have some sort of issue, basically, if that pressure rises up, then your vessel pressure is going to rise up as well. Most of these systems are set with a high pressure set point of about 510. So you don't really have much leeway. It wouldn't take much to get your CO2 pressure up there. And basically, like I was stating before, they have an auxiliary condenser in case there is some sort of failure. Every time I call the manufacturer, like, well, just set it to where it probably was going to work good. And I was like, okay. So if you figure it goes off on high pressure at around 510, The relief goes off at 585. So basically, I've been setting it around 540 to prevent any kind of, pop off, with the CO2. Anything you want to add?
Yeah. So with that, I would start setting those condensing units at like 510. So that way, when the high pressure is going to kick on, it's going to start up. I would actually set it a little bit lower than that. So that way it can assist and it can bring the vessel back down so it doesn't spiral out of control and you have like a fast relief go. So, 480, if you can keep it, the lower you can keep it, the better. And if you got to kick on the auxiliary unit every once in a while, it's not that big of an issue. So I would set it a little bit lower. I want to talk about heat exchangers a little more. So with these heat exchangers, they are designed for gas only. If you start pushing liquid through them, they're going to be too small and you're going to have a huge pressure drop. They're not designed to push liquid through these condensers for the Cascade side of the CO2. So if you are running a desuperheating valve, this is where the problem comes in. You really got to watch is you don't want that desuperheating valve to cause you to condense into a liquid. You want to be slightly over, what you're going to be condensing at, because if you do that, that heat exchanger is going to have a huge drop on it, and it's going to greatly affect your high side refrigerant rack. You're not going to have enough load to keep everything running. And this whole Cascade thing is all about load management. You want to keep your CO2 load steady so you can keep your Cascade primary high temp steady. Because if you're cycling on your high temp rack, it's going to cause vessel issues and receiver pressure issues and high pressure issues on your CO2 side. So the more steady you keep this whole thing, the better it's going to run. So load management, once we start building more on the CO2 side, is the number one most important thing with CO2. So that means defrost schedules, no overlapping large defrosts. When stuff's coming out of defrost, stuff needs to be going into defrost. So that way you're, bringing on load and taking off load. So that way you're not shocking the rack and, dropping, say like the walk-in freezer goes in defrost and then you're putting some glass door cases in and then all of a sudden they both come out of defrost at the same time. Now you're going to have this huge load increase and more than likely the high stage rack is not going to be able to keep up with it, or you're going to have some cycling issues. So like Brett said, it's going to have a lead stage VFD compressor, hopefully, or a digital. But just keep in mind, you're talking rapid load changes if it's not set up properly, and you want to try to keep those rapid load changes down to a bare minimum. And then the EEV tuning for like the actual condensers themselves. Now that is a huge issue. A lot of time needs to go into that EEV tuning. And I don't know, you've done some of the bullseye stores, I'm sure, Brett, and I'm not going to lie, like the way a lot of them, so far I've looked at like 3 or 4 stores, they all have stock XM controller setting PIDs in there and throttle ranges, and it doesn't work that great. I've tuned a bunch of those valves. It takes some time. If you really sit there and tune that valve out, it'll work like perfect. You should see like a steady line going through it. It shouldn't be jumping from 0 to 70%. If it's doing that on the EV, you're going to have very poor CO2 control.
So a couple things that you touched on. So just for example, you were talking about the liquid being created. One of the things I have seen, we had a store that had a desuperheating coil that was outside, and basically it was up on the roof. So, the thing would just turn off and on the fan based off demand, based off of pressure. In the wintertime, in the middle of winter, what would end up happening is exactly what you were talking about. It would be fairly cold here. Wind would be hail, just going right across the coil, and then actually causing the vapor to condense into a liquid. And then at that point, it causes a pressure drop. And because there's no vent line, basically, in the receiver, basically that pressure gets bigger. The discharge pressure gets bigger, and it just exacerbates itself. So we actually had to go through and actually put a bypass around the superheating coil to make sure that wasn't going to happen anymore. Also, as far as the EXV tuning, you have to look at the sizing. A lot like you said, startup guys, should spend more time with, tuning the thing out. But a lot of times these things aren't bid for that. So basically what will happen is, you could have a valve that goes from 0 to 100 constantly, which is causing, just a crazy load coming back to the rack. I went through and, if you find out, basically, let's just say you have 60 doors of frozen food, you can figure out basically what the size of that valve is for those doors and basically program that 5-door the same that you would that 5-door on that case controller. So you get, a good superheat back. So it's not basically just sitting there starving and flooding, and then just causing an influx of load on the whole rack. Same thing with the load management that you were talking about before. We had a spike at 9 o'clock on the CO2, 9 o'clock in the morning, 9 o'clock at night. And come to find out, it was because we had 5 systems going in defrost all at once on the CO2 side. We had basically the main freezer, the seafood freezer, the bakery freezer, 20 doors frozen, and like some meal deal thing. So basically there was just a mass quantity of CO2 coming back, and there's no way that basically the DX side, could bring that pressure down fast enough, because of it just couldn't. There's too much BTU per pound in CO2 versus, a DX refrigerant. So it's hard for it to, basically be able to pull that load down fast enough.
So yeah, one other thing with the whole load management thing, and you touched on the superheats of the case controllers. Like, so now that we're actually getting into compressing CO2 and oil management and stuff, I want to talk a little bit about superheat control. Once you get down to about 10 degrees of superheat, I mean, CO2 and oil will, I'm going to mess this word up because I do it every single time, miscible. I don't even remember if that's the right word. They mix very well together. So once you get down to about 10 degrees, you will actually see, once your superheat's down about 5 degrees, it'll actually carry the oil out of the compressors, and you'll start pumping oil like crazy. So you need to really watch it. You want to be about 20, 25 degrees on your superheat coming back to keep those compressors protected now, and to keep your oil from flowing out. You want to really keep an eye on your discharge line temps too. When you start getting low discharge line temps, that's an indication that you're getting some flood back, depending on how severe it is. So you just want to really watch that superheat control. And if you're using the Emerson stuff and you have like the XM678, 679s, you really got to watch out, because if the EMS guy didn't program in the temp sensor alarms, you could have failed temp sensors. I've seen the PB6 temp sensors for the Dixel controls reading 135 degrees on the suction line temp, and you're flooding back like a banshee, and you're having oil issues. And it may not show up as flood back right away to you. I mean, or you can't keep up with oil, and it's because it's washing it away faster. So like one big tip, if I'm looking through and it's on an Emerson system and I'm having massive amounts of flood back, the first thing I'm usually going to check is the case controller suction line temp sensors and the transducers. So the easiest way to do this is if you hit menu 5 and then go into the case controllers itself, and just hit control page down, and just keep hitting it. You'll scroll through every single case controller in the store. Now, when you're doing that, you want to look at your suction pressure. All your suction pressure should be almost the exact same, because they're going to be reading a a common suction pressure from a loop. And then your suction line temperature should be pretty close. I mean, as long as they're operating, the EVs are operating properly. If you see one that's at 80 degrees or whatever suction line temperature, and it's not in defrost, that one's probably causing your flood backs. You want to look. I mean, Hill was using some cheaper temp sensors. I'm not really sure where they got them from, but we did a string of stores, and I think I had like 11 fail in like 2 weeks out of startup. Started reading like 100 degrees. So that's one thing to keep in mind. And just like a normal TXV bulb, you want to strap these things to the suction line, insulate them if you can. Try not to use zip ties. I mean, it's all you got is zip ties, and use zip ties. But you want to strap them to the suction line, insulate them if you can. And then big thing too, I see this get missed a lot on startup, is suction transducers not getting opened. And if they're not changing, so what ends up happening is eventually that transducer packed angle valve bleeds through enough where it actually reads like 400 pounds, right around where it should be. But it's not correct because it's actually the transducer's closed and it's just CO2 leaking through the packed angle valve. So that's one thing to keep in mind. And you really want to make sure those EEVs, or if you have the unfortunate thing of having pulse valves, then you want to make sure those are tuned and spend a little bit of time tuning them. Like Brett said, I mean, it may take some time. Once you get some solid numbers, I mean, you can pretty much use those numbers for just about all of them. It just takes time figuring out your PID settings and all that stuff.
So, we were talking a little bit about Emerson. One of the things, there are other case controllers that do the same thing, basically just modulate superheat and, adjust per, what you're trying to accomplish. RDM, they are using a temperature sensor basically on the suction line, obviously, but also they're using a temperature sensor on the distributor tubes. Years ago, that Emerson made a case controller called the CC100, and that's basically how it figured out its superheat. Because basically your distributor tube is, going to be, your saturated temperature of your refrigerant. So if that temperature, a lot of the temperature sensors coming in from the factory, they're actually putting in between the actual either the pulsing valve or the bipolar stepper, in between where the nozzle is and the TXV. Well, right there, that's still basically liquid pressure. So you're not actually going to get a true blue saturated. So basically your case is going to technically starve because it's not getting an accurate temperature. So just be mindful if it does that have that kind of control, that the temperature sensor is actually on the distributor tube leading into the coil, not in between the nozzle and the EXV.
So you could actually do coil in, coil out with those, with the Dixel stuff too. Nobody really does it because it didn't really work that good 20 years ago. But apparently we just, keep repeating the same mistakes, AKA pulse valves. Those didn't work 20 years ago, and now they're back. One thing to really watch out for those pulse valves, I'm sure most guys have seen it, is they make the liquid line shake in the store. So you really got to, pay attention to your strapping and stuff. We had a store where it was moving at least 3 feet in the hangers at one point on startup. The pulse valves were pulsing that much, and it was causing the mains in the store to swing back and forth, and everything was to spec. And some of the stuff already had ERFA straps on it and everything else, and it was still moving. So, I mean, just be mindful of that, like when you're doing your clamping and other stuff with pulse valves, to make sure that you have proper hangers. And then one other thing I want to go over. So with is it the 678s or 679s, Brett, that are the steppers?
You're going to give me the line.
I think it's the 8s.
678 is the bipolar stepper. 679 is the pulse.
Okay, so I don't know if you guys have seen this, but we've had a rash of valves that ground out, and they somehow put 24 volts through that stepper motor and onto the Modbus network, and then it ends up blowing up the E2 PIB board. I've had this happen like 5 times now. So on startup, I mean, no customer pays for this, but like they're like $25. It's a RS485 line isolator that you could buy, and basically it's like a repeater, like for a Modbus network. They're on Amazon. They're like $25. It's an RS485 line isolator, or repeater basically. But what it does is it isolates the signal from the Dixel controllers to the E2. So basically, if your controller takes a dump and somehow the valve causes the short through there, and now you only lost one controller, because the Dixels don't seem to all short out. It's usually just one, and then it takes out the PIB board on the E2, which is going to be your power interface board where all your COM ports come into. Now, you would just end up burning up this RS485 adapter, which is $25. Without a PIB board, you're not going to run that E2, and you're going to have a very bad night. So that's just one thing to kind of keep in mind if you guys are losing PIB boards. They're shorting out for a reason. It's the case controllers and the EEVs. It's the case controller killing the EEV, then the EEV kills the case controller back. It's like a murder-suicide thing.
Yeah, and basically, I didn't think that this was possible. So you have like the regular, master network basically that connects, via the Modbus, through back to the case controller. And then you have a secondary network, so like basically, let's just say you have a circuit that's A01A and then A01B and then A01C. Well, A01A, B, and C aren't all going to be on the master network, just A01A. Well, there's a sub network that basically gets piped in, that gets wired in from A, B, and C. I did not know it was possible for the short through the EXV to actually go through the local network in between the case controllers and go all the way back up the main Modbus line and then take out the PIB board. And there was no way to figure out. There was no, at that point, nothing is communicating. So basically, you're at the mercy of trying to figure this out. One of the things you can do is if it's medium temp, you might luck out because it probably hasn't defrosted for a couple hours. So at least you can actually look at the suction lines and see which one has the most frost on it, and kind of figure out that way. Maybe what case controller actually took that line out on that comm loop.
Yeah, or you get lucky and there's a hole in it because it burned up that bad. I've seen one do that.
What's that?
Burned up so bad that there's a hole in it, like right where the network connection is.
No, the only thing we saw is the resistors right underneath will light bright orange for about 2 or 3 seconds, and then that's it. They light up and let the smoke out.
It's an expensive smoke experiment.
Hi guys, welcome to the Advanced Refrigeration Training Podcast. I'm your host, Kevin Compass, along with my partner, Brett Wetzel. Today's episode is sponsored by Westermeyer Industries, the leaders in oil management and pressure vessels for the commercial refrigeration industry. Whether you're involved with designing a system or tasked with servicing one, Westermeyer Industries has been helping meet the needs of customers like you for the past 20 years. They offer a broad catalog of stock system components with an in-house team of engineers to assist with custom solutions as well. From oil separators and heat exchangers to system monitoring devices, Westermeyer Industries are a total system specialist with industry expertise, engineering know-how, and the manufacturing muscle to help you tackle problems and deliver solutions.
With this Cascade stuff, you're going to have mostly electric defrost. I mean, you could do hot gas defrost with this. You're in the realm of completely possible hot gas defrost with the differential valve. I have yet to see anybody do it, but I'm not going to say anybody's not going to do it. It's completely doable because you're going to be under that pressure limit, and you could use discharge gas from the CO2 side to do your defrosting. So that's completely possible. I mean, you could have a DDR or a defrost differential valve. More likely, it's going to be a stepper valve doing it, or you're going to have electric defrost. More than likely, you're going to have electric defrost. When you start bringing hot gas defrost into CO2, this is when it starts getting complicated and starts making more issues sometimes than it's worth. But with this setup, you can have hot gas or electric defrost. I mean, you're not going to have pressures very much higher than 410A. It's going to run like a really efficient high 410A system. Now, when you're bleeding things out, same precautions as servicing a normal CO2 system. So you're going to want to, pump it down. You're going to want to get it down to like 75 pounds. You want to get all the liquid out of it, get it down to like 75 pounds. Shut off your suction. You're going to want to let it, blow till it gets like 75 pounds and kind of stop, watch it. If it starts rising up again, you got some liquid in there, give it a few minutes and then blow it again and then do it again. And then you're going to be okay. If you make dry ice is no big deal. Everybody makes dry ice out to be like it's the end of the world. You make dry ice, you raise the pressure back up, the dry ice is gone. Just like that.
So one of the things I want to say about, we talked about when we were talking about pump liquid, we were, telling, that we could just basically just let the pressure go and let the pressure go into the, into the suction because there was no compressors to damage. Now that we actually have compressors to damage, and because they're so critical with the superheat, the way that I charge, especially if the racks are up on the roof, I'll find a case that is basically, close to wherever I'm at, close off the liquid line until that liquid line, stops sweating until, basically the temperature starts rising. Then I don't have any more liquid in there. Use my gauges to basically then purge out a little bit of vapor CO2 that I do have in there back into the vessel or into the cylinder that I have. And basically now I'm actually the liquid supply. I'm actually taking the liquid CO2 from the cylinder and charging it directly into the liquid line. Because if I just dump it in the suction line, I have to worry about potentially damaging and sending liquid back up to my compressors. If I'm letting the EXV or the pulsing valve, control its superheat the way that it should, there's no way that there should be any damage, right? I'm letting the valve do naturally what it's supposed to be doing. You just have to make sure that you don't overcome the pressure in that line high enough that you're going to hit a relief. Some of those reliefs on the systems, like I said, are like 585. And if that cylinder is, 87 degrees or, you're going to hit 1044 PSI. So you have to be careful that you don't overpressurize the system and blow the relief down in the piping. But basically that's how, I end up charging that system, closing the line off, connect it right to the liquid line and letting the, the expansion device do its job and meter that refrigerant in.
Yeah, one thing I'm gonna tell you guys, really be careful, and it almost got me pretty good. We have a customer that doesn't want any liquid shredders in their cases because we end up having leaks, and what happens is guys throw their reagents on and shredders stick sometimes, and then you get a guy that's going to burn himself, like a newer guy. Or if you have a shredder stick, I'm just going to throw this out here for everybody. If you ever have a shredder stick, please do not try to put the hose back on. Every year we have like 2 or 3 guys that end up going to the ER because they try to put the hose back on to save the gas. Nobody cares about the refrigerant. Okay, the easiest way to do this without burning yourself is to go get a core puller. I always have a core puller in my bag. You take the guts out of the core puller, the actual pin remover. You open it up. You put the core puller on the Schrader like you normally would on the cap. You screw it on with a pair of channel locks so you're not touching it, and then you shut the ball valve on the core puller. That is the easiest, safest way to isolate a stuck Schrader. So that's one way to take care of it. But we, at this particular location, they had us remove all the Schraders, the liquid Schraders on the cases during construction to reduce leaks. Well, what happened was I had the EEV fail. I pumped the thing down. Well, in between the liquid ball valve and the EEV, there was no port. So I had assumed that the valve was dead. Well, I got the suction down, everything was good. Well, I nicked it with a tubing cutter on the valve body or the valve extension, and lo and behold, there was still 500 pounds of pressure there, so full of liquid. So just be careful. I always nick the inlet to the valve with a tubing cutter, because if that EEV has failed, you are not going to be able to get that pressure out of there. You got to nick it and let it bleed out. Don't take a torch to the inlet and start unbrazing it. You're going to have a small pipe bomb.
So one thing about high pressure or any kind of failure that you have on the CO2 side, especially the high vessel pressure, just like we stated before with the pump liquid, there is a sequence of events that happens once you have a shutdown. If you do have a high pressure event, basically it's going to shut down the enables to all the case controllers. Like I said before, usually in CPC, they use a flexible combiner that basically is going to shut down every single enable on each of the EXVs on the case controllers. It'll change the set point and then stop it from working. Then basically what it'll do is it'll start bringing each circuit on every 3 to 5 minutes, just so you don't have that large influx of just, hey, we're going to turn everything back on at the same time and potentially raise that pressure exponentially and end up causing another high pressure event. This is to help the vessel get under control and keep bringing the systems on surely but slowly, so we still have a load on the CO2.
Yeah, it's one thing you really want to pay attention to when you're bringing everything on. So make sure to start it up slow and make sure your primary is running first and ready to go. So one thing I've seen, which I know you've probably seen too, is when the customer's using that primary refrigerant also in the store. We ran into this the other day, and the way that they were set up. So like, obviously we're trying to run a 25 degree CO2 temperature with like Brett said, it's around 7 degrees. So you figure you're going to be like 18 degrees, 17 degrees. So maybe even colder depending on what it is and depending on what their design is. I mean, the design could be, run a 15 degree evaporator. Well, that ends up being less than your primary cases. So then you get in this like load issue with the cycling, because now your primary cases, especially if they're on case controllers and they're controlling temperature with the EEVs, you get this load issue because now all your coil TDs are off and your saturation temp is way lower than it needs to be. So you get this starving of the rack basically for load, because everything is satisfied down in the store on the medium temp. So all you have is the CO2 side. So the higher you could float that suction pressure and keep that vessel satisfied and good, the better. So that's one thing you got to really keep in mind when you guys are doing this and doing your actual load control and startup. So you want to try to keep that suction pressure as high as you can. So these high efficiency, 513A, 134A, 449, whatever it is, those cases don't start satisfying on EEVs. It's why I'm not a fan of certain case controllers, because they want to control temp and superheat when really we just needed to control superheat, and temp should be controlled with an EPR. So that way we can keep the load constant. But we end up having to run a lower saturated suction temperature to run the CO2, and that becomes a problem.
If you are going to float or try to float something on the medium temp side, float it off the actual vessel pressure. The vessel pressure is maintaining. That's typically going to be your lowest SST out of the whole bunch. If you look at a refrigeration schedule, basically, you have to be able to maintain your saturated to maintain your discharge pressure, or I'm sorry, your vessel pressure / discharge pressure on your Cascade. So make sure if you are going to float, preferably probably float it right off that vessel pressure to make sure that that's maintaining. All the rest of the stuff will follow.
Go ahead.
No,
the easiest way with a E2 to do it is just make a fake circuit and call it vessel float or whatnot, and then assign that to the rack. And then I would probably go with a faster reacting float, maybe 2 to 3 minutes float interval times, because you want that thing, if it needs to stage down immediately. You're not gonna, it's not like a case where you're going to have an 8 to 10 minute float interval, before it starts changing pressures. I would go a little bit, faster reacting.
Also about having all these electronic valves, especially if they're bipolar valves, you want to probably reset them at least once a week. You can do this easily with a time schedule. Basically, whenever it hits X time at this day, basically give it a closure command to shut down. You don't want to do, if you have 3 heat exchangers, you're obviously not going to turn off all 3 heat exchangers at the same time. Stagger them by about 15 minutes to a half an hour and let it actually, come back down the temperature, because you're basically going to cause that pressure to go up a little bit higher.
So one other thing that I want to go over, if you do have an older system, and you have the Hill Phoenix, dongle looking things, what are those called? The SMS controllers?
SMS, yeah.
Piles of junk. So just get rid of those and put some Sporlan Calvin 2s in, or some, I know people have done 678s. I'm torn between this, because the Sporlan controls superheat a lot better, and it only controls superheat, and that's all I want. And then you get the 678 that wants to control temp. I would probably honestly rather go with the superheat controller, because it's going to work better. But you could also go with the 678. So I'm going to caution you guys with the 678. So the 678 wants a temperature input to control actual temp. So instead of making it leaving CO2 temp, like I've seen these manufacturers do, which is stupid, because then eventually the case controller starts fighting the CO2 temperature. So it starts cutting back. It sees the CO2 temp come down, so it starts cutting back your EEV on temperature instead of superheat, and then you get a load increase, and your chiller's not flooded out enough to be able to handle that load increase, and you get this hunting. So the one I do for that is I send the EEV a fake set point, or I send the case controller a fake set point, instead of linking a set point, a temp sensor to that. I'll give it a fake set point of say minus 15. And something it's never going to be able to hit. So it's always going to be controlling superheat instead of controlling actual temperature. So you want to give it a fake set point, and then that way that controlling temp sensor, temperature 1, can't ever hit that temperature. So it's always going to be controlling superheat. That way your coils are properly flooded out and ready for load increases. Flooded coils are better than non-flooded coils, because if those coils aren't flooded and you get a load increase, you're not going to be able to react fast enough in order to flood that coil in order to pick up that heat from that load increase.
Also, you have to make sure that, your pressures don't get too low on your DX side. There are some refrigerants, 134A, has a stupid, heat exchange rate, especially if your delta P across your electronic valves, starts going real low. So make sure that, we've had a problem with, it didn't have a minimum set point as far as the saturated that it was trying to maintain the wintertime. And basically, once the 134A got down to 80 psi or 75 psi, basically the valves then at that point as well weren't big enough to actually achieve, and maintain the load coming back from the CO2. If you do have an option, if they, if someone tells you that they want you to put in the Sporlan subcool control rather than the superheat controller, don't put in the subcool controller. Just control the superheat on the heat exchangers. That's what 99% of the case controllers that operate those heat exchangers, that's all they're worried about.
Yeah, and you're still going to have to tune the PIDs. Yeah, the one that's in there is like somewhat okay, but you're still going to have to tune the PIDs. Read the instruction manual. The Sporlan one's really easy. So, but still tune the valves. I want to go over the oil system real quick, and we'll probably wrap it up. So the oil system, you're going to have a coalescing separator. Could be pretty large separator, small separator, and you could either have a separator reservoir combo, and you could be feeding out of the reservoir. We're not going to have a float. We could have an optical eye, and a solenoid or a stepper valve to feed the oil out to the reservoir. Generally, you're going to vent the reservoir to the flash tank. So your receiver pressure is going to be your oil pressure.
And that's in transcritical. In this instance, in Cascade, typically all it is it's basically a coalescer. That's a separator and reservoir that basically just goes to an OMB controller controlling the level in the compressors.
Yeah, a standard OMB or an OMC control work fine. So, yeah, that's your oil system. Go ahead.
CO2 compressors, the Bitzer ones. Oh, what the hell's the oil? 85. Help me out here. I'm having a senior moment.
It's 85 weight. I don't use that Bitzer oil. I get the oil from the supply house. It's 85 weight, like CO2 weight oil. It's 85 HH oil. It gets CO2 rated oil, but like the oil from the supply house is half the price of the Bitzer stuff. And somehow, at least it was last year, Hill Phoenix owned like the majority supply of Bitzer's CO2 oil, so you had to buy it from them. So they were marking it up, so that upset me having to get it from them. So we ended up getting it from a supply house instead. If you're doing a lot of CO2 work, you're probably going to want to keep some oil on hand. The Copelands use the same oil. Or no, they're using. Were they using 32 weight?
I can't attest to that. I've honestly all the Cascade racks that we have Bitzers. Every single damn one of them.
So our the only Cascade rack I know is 32 weight on that one because it's actually 410A scrolls. They're using 410A scrolls for the Cascade side or for the CO2 side.
Oh, okay. Which
actually Aldi does for their transcritical racks for their low temp. They run CO2. They run 410A compressors.
Are they doing? Are they able to do digital unloading on those compressors, on those 410A compressors?
Yep. Yes, sir.
Because unfortunately,
it works pretty decent.
Because the other night I looked up, call it a boring night. The other night I looked up the VFD rating that you can do on a scroll, and basically there's not much give and take. Like with a reciprocating compressor, you can go from, on a Bitzer, most of them you can go from 25 to upwards of 70 hertz to eke a little bit more capacity out of it. But the scrolls, man, I think it was like 40 hertz to 60 hertz. Like there wasn't that much play, with actually, with trying to play with it with a VFD.
Yeah, it's because of that bottom bearing, the way the oil slings. I mean, you can't get much out of them. Emerson just released a bunch of scrolls where they could push them farther, but I mean, with a scroll, you can't beat digital unloading compared to a VFD. I mean, in the CO2 application, it works great. I mean, I honestly like the Emerson CO compressors more. I think they are a little tougher than the Bitzers. So, I mean, we've done a couple Emerson racks with 4D compressors, and they run great. But yeah, like the oil system, just OMBs or OMCs. I mean, most of the OMBs, it seems like they're getting, faded out now by the OMCs, which is just another Emerson brand. But yeah, just a standard setup of oil. I mean, it's just a lot higher pressure and a lot messier. So, I mean, just to make sure those filters stay clean and just every year getting them clean. Brett, do you guys have liquid dryers or are they on the suctions?
Yes, we do have liquid dryers. There's usually
one thing that. So liquid dryers are usually the only time I ever make dry ice in something. What I generally do if I'm changing liquid cores is I shut the inlet to the liquid core, and then I will take discharge gas from a compressor and I will feed it into the liquid core, and I will heat the liquid core up above dew point. Whatever point is outside, so the liquid core is warm and it's full of discharge. Then I'll shut the outlet of the valve or liquid core. Then I'll suck out the CO2 back into the suction. And generally, you start blowing it off once you get the suction. You won't make dry ice in there. You'll heat that core up and push all the liquid out, and now you just have discharge gas in there. So, I mean, if you just try to do that and pump it out, you're going to have giant dry ice chunks. You're going to have to deal with that. And now you have a freezing cold shell that's going to attract moisture, and then you're going to have moisture issues. Big thing is pull vacuums, get it nice and tight systems. Just every time, no purging anything, because can't believe I have to say that to people. But you want to make sure that everything has no moisture in it, or else you're going to have oil, and you're going to have carbolic acid in the oil.
I still can't believe you have to say that. No, guys, I think we covered it quite extensively. What I'm going to do is on the Advanced Refrigeration Podcast Facebook group, I'm going to post some of the piping diagrams, so you guys can actually see, how this thing is piped in, whether it be with the de-superheating coil or the three-way modulating valve to maintain that de-superheated temperature of 95 degrees entering the heat exchangers. There's a lot of other, heat exchangers, suction to liquid heat exchangers throughout the system. They're all over the place. The piping can look kind of confusing, so just be mindful of that.
Yep. All right, guys. Have a nice night, and thanks for listening.
Thanks, guys.